Assalamu alaikum. So in this lecture, we'll start with the next type of curve, which is a compound curve. So like we discussed in the introduction, that compound curve is basically a combination of two or more simple circular curves. Now, it's not one simple circular curve because in a single simple circular curve, the radius of the curve remains constant. So if this is the curve that we're talking about, so at every point of the curve, the radius would remain the same. However, in a compound curve, as you go along the circumference or the length of the curve, the radius would change after some time. And then it would remain constant because then it would be another simple circular curve. And then again, at some point, it would again change. So it's basically a combination of two or more simple circular curves. Now, why do we give a compound curve? The reason is that sometimes the land accessibility dictates that you cannot give one simple circular curve. Sometimes you need to keep the radius of the curve different at different points. You want to change the sharpness or steepness of the curve at different points because it's not just about laying out a curve. Once you give a curve, the traffic that's moving on that curve, or it's either a railway line, the speed has to be maintained according to the curvature. So if you give lesser curvature, if you give super elevation, then it means that the speed with which the vehicles can move from that curve increases. Otherwise, they'll have to maintain a lower speed. So usually, whenever you go along a curve or travel on a curve, you would usually see a speed limit given there. And the speed limit changes based on how steep the curve is or how good the super elevation is, and a number of other factors as well. So that is why there are some reasons that you need to give more than one simple circular curve, and that would be called as a compound curve. Now, if you see this figure, from we want to give a curve between these two lines. So AB is your direction of travel, and BC should be your direction of travel afterwards. Now, like before, these are two lines which are intersecting at the point B. Had there been no curve, and the angle of reflection, like before, is phi, and you want to join these two lines with a smooth curve, and the curve is starting at the point T1 and it's ending at the point T3. Now, the difference is that from the point T1 to the point T2, the radius of the curve is smaller. The radius is RS, and it's a smaller radius. And from T2 to T3, the radius is more. So basically, now we have two curves. One that goes from T1 to T2, and then we have a curve that goes from T2 to T3. And from T1 to T2, the radius remains the same, and from T2 to T3, the radius again remains the same, and it's a combination. Now, in order to solve this curve, an easier way is to forget what is on the either side of the curve. So if you, from the point T2, if you forget what's over here and just look at this portion. So if you look at this portion, it's just a simple circular curve, like we did, whatever we did before. So in this case, the tangents would be, or the lines would be AD and DE. So suppose these are the two lines that you want to join, right? And the angle of deflection would be phi 1. Let's call this phi 1. That's a misprint over here. And the lines T1D would be the tangent length, and T1, T2 would be the length of the curve. So it's exact replica of whatever you've done before. And if you look at the other side, now if you forget whatever is over here and just focus over here, now again we have another simple circular curve which has angle of deflection phi 2, and starting from T2 going to T3, and again this length will be the tangent length, and just simple procedure whatever you've done before in simple circular curve. What's different in this curve is that when you combine them, um, you have some additional equations that you can use. So one additional thing that we can use is this line DE. Now, T1D and DT2, these are tangents of the first simple circular curve. T2E and ET3, these are tangents of the second simple circular curve. But this distance, DE, is the common tangent. We call this as a common tangent because this line is tangent to the first curve at the point T2, which is the ending point of the first curve. And this line is also tangent to um, T2E at the point T2 again, which is the beginning of the second curve. So this line DE is called as common tangent. So we can use that. And then we have this triangle over here, BDE, which can help us in determining some other factors as well. Now, remember that what they've written over here is these two tangents. So these are the tangent lengths of the the whole bigger curve, the combination of the two curves. So it's a tangent length of that. And the tangent length T capital TS is equal to the tangent length of the first curve plus this distance BD. And we'll get to that, how can we calculate it. Why do we have to calculate these things? Because once you go in the field to layout, you'll be starting from T1, right? Or you'll be starting from point A. From the point A, you'll sketch this line, you'll reach the point B. So you would have the direction, but you would need to know that where is the location of point B on this line. On the line AB, where is the location of the point B? So for that, you will choose the starting point of the curve as T1. From there, you will measure this distance. And if you have this distance, capital TS, then it means you can lay out this point B in the field. Then, by using the deflection angle, you can find out the direction of the second line, or you could have that in the field. So that's not a big problem, but you can calculate the distance again, and you can find out this point T3. And then by using this tangent T1B, you can then start laying out the first curve until you reach the point T2. And then from the point T2, you can start laying out the second curve. So that is why it's important that we find out all of these things. So now let's see over here that what are the different factors that we have to find out. So these are definitions. Some of them we have already discussed, and if not, I'll come back to those or I'll refer to those. So calculation of data. So first thing is that deflection angle phi is equal to deflection angle phi 1 plus deflection angle phi 2. Now you need to see what these are. So phi is the deflection angle of the bigger whole curve or the combined curve, compound curve, and phi 1 over here is the deflection angle of the first simple circular curve, and phi 2 is the deflection angle of the second circular curve. Now, if you see over here, they form a triangle BDE, and from here you can see that phi is equal to phi 1 plus phi 2, because the exterior angle of a triangle is equal to summation of two opposite interior angles. So from that, we get phi is equal to phi 1 plus phi 2. Okay, then we have, they're using this triangle BDE. Basically, what they are trying to find out is the tangent lengths of the combined curves. And for that, like I wrote the equation before, you have the tangent length of the individual simple circular curves, plus you need to add some distance. So if you want to find out the tangent length, capital TS, or the length T1B, so for that, the length would be addition of the tangent length of the first simple circular curve plus the distance dB. Now we don't know the distance dB, and we have to find that out. So for that, what they're doing is that they're using this triangle BDE. And if you remember, from trigonometric properties. So over here, triangle BDE. So if you remember, um, I think I should draw this figure over here so that we don't have to go back again and again. So this is the triangle that we're talking about. And over here we have the angle phi 1, over here we have the angle phi 2, and over here we have phi. So we have D over here, B over here, and E at this point. Now, by using this, what they're doing is that they are taking the trigonometric relations of sine, and that means that the side BD divided by sine of the opposite angle, which is phi 2, is equal to the side BE divided by the sine of opposite angle, which is phi 1, is equal to the distance DE, which is the common tangent, divided by the sine of the angle B. Now, since we don't know this angle B, so what we can do is we can use 180 minus phi, something that we've used before, or if you're using this triangle, that would be 180 minus phi 1 plus phi 2, and we know that phi 1 plus phi 2 is equal to phi, so it makes basically the same thing. What we are interested in finding out are the distances BD and BE. So from this relation that we have over here, we can find out BD with reference to DE. So BD would become DE multiplied by sine phi 2 divided by sine of phi. How do we get sine of phi? Because sine 180 minus phi is equal to sine phi. So this is a trigonometric identity again. And similarly, in order to calculate BE, we have DE multiplied by sine phi 1 divided by sine phi. So these are few equations that you would need to remember. Then we have the curve length. So the curve length for the short curve, the relation that we used before, which is pi r angle of reflection divided by 180 to convert it into radians, which is basically, if you remember, length is equal to radius into theta. So just by converting that into radians, so you get pi by 180 multiplied by that. So in that sense, we can calculate the curve length for the short curve and the curve length for the long curve. Then we have the deflection angle equation, same that we used before. So you will be using it two times. First times for the short curve, and they're calling short curve as the curve with the smaller radius. And then for the long curve, the curve with the longer radius. So again, the chord lengths would be different for both depending on the curve length. And you know how to do this. We've done this before. Then we have change of the point T1, which is change of the point B minus TS. So if you want to calculate the changes, and usually what they do is that they give you change of the point B. From the change of the point B, if you subtract the tangent length of the combined or the compound curve, you get change of the point T1. In that, you add the curve length of the smaller curve, you get change of the point T2. And in that, you add the curve length of the larger curve, and that brings you to the change of the point T3. So it's pretty much similar to what we have done in the previous lecture of simple circular curve. So that's it. Let's now see the question and see how they've done it. So the question is that two tangents AB and BC intersect at the point B. So these are the tangents of the compound curve. Another line DE intersects AB and BC at D and E such that angle ADE is equal to 150 degrees. So that means they've given a figure, so that makes it pretty much easier. But you should be able to construct this diagram even if it's not given, just by reading the statement. So you should know how to do that. So what they're saying is that the angle ADE is 150 degrees. So that means phi 1 would be equal to 180 minus 150. And then they're saying that the angle DEC is equal to 140. That means that phi 2 would be 180 minus 140. And the radius of the first curve is 200 meters, and that of second curve is 300 meters. The change of the point B is 950 meters, and we have to calculate all the rest of the data. So in order to proceed with this, the first step was to calculate phi 1 and phi 2. We've done that. And the next step would be to calculate, sorry, the next step would be to calculate phi, and phi would be equal to phi 1 plus phi 2. So now that you have the deflection angles phi, phi 1 and phi 2, the next step would be to calculate the tangent length of the bigger compound curves using the tangent lengths of the smaller curves or individual curves. So for that, the equation that we used before, the length BT1 would be equal to this distance, which is basically the tangent length of the simple circular curve, which you remember is R into tangent phi by 2. So if we convert it into in terms of the smaller curve or the curve with the radius 200 meters, so did denoting its radius with RS, which means the radius of the smaller curve, and this would become phi 1. So this is the tangent length, and in that we need to add this distance BD. And if you remember, we had an equation to calculate BD. So just replace the values and you would get that. And similarly, for the tangent length BT3, again, that would be the radius of the longer curve into tangent phi 2 by 2, like we do before. And then you'll have to calculate this distance BE using the same procedure or the equation that we had before. And after that, you'll have to calculate the curve lengths, and then we can calculate the changes. So let's see. So phi 1, 180 minus 150, like we did, 30, and phi 2 becomes 40, and phi becomes 30 plus 40 is equal to 70 degrees. Then they calculate T1D, which is the tangent length of the smaller curve. So that is RS tan phi 1 by 2. You've done this before. Similarly, the tangent length of the longer curve, T3E, which is equal to ET2. So the equation, and we get the tangent length for the longer curve. And then we calculate DE, which is the length of the common tangent. And the like we saw before, it is simply the summation of the tangent length of the smaller curve and the tangent length of the larger curve. So we get DE. And then from triangle BDE, in order to calculate these distances, BD and BE, use the relation that we had. You can get that, and then we get the tangent length of the combined curve or the compound curve. From there, what they've done is they've calculated change of the point T1. So what we were given was the change of the point B. From that, you subtract BT1 or the tangent length of the curve, the combined curve, compound curve. And from that, you get change of the point T1. Then we calculate the curve length of the shorter curve. So if you remember, we just discussed the equation pi r into phi 1 divided by 180. So we get the length of the shorter curve, then the change of the point T2, which is T2 is the point which is the ending point of the first curve and starting point of the second curve. So in the change of the point T1, you add the length of the shorter curve in order to get change of the point T2. And in that, you add the length of the long curve in order to get change of the point T3. So then we have deflection angle for the short curve. Now, if you remember the concept for the chord lengths, so the chord lengths depend on if they've given you the value, or if they've not, you can choose any interval 10 meters, 15, 20 meters. Obviously, your work would increase if you decrease the interval, but accuracy would keep on increasing. So in our case, the length of the short curve is 104.72 meters, and the interval that we're taking is 20 meters. So that means we can do this work in 5 chord lengths. That would get us to 100 meters, and then we would be left with just the distance 4.72 meters. So that 4.72 will become our subchord, and the 20 meters would become our full chord. Just replacing the values in the equation for finding out deflection angles, and then apply the check. So the sum of the deflection angles should be equal to phi 1 by 2 or phi by 2, the angle which is at the beginning divided by 2. So once you've done that, you can apply the check, and similarly, you can do the same procedure for the second curve. And for the second curve, they take an interval of 30. Let's see if they had this in the question. No, they didn't. So you can choose any interval. Um, that depends. Usually it's given. If it's not given, it can be 10 meters, 20 meters, 30 meters. It can be any value. 30 meters is fine even. And they've used that, and then they apply the check. So this is how you find out the different values for setting out the curve, because what you would need is you would need to find out the location of these points, the point B, the point T1, the point T3, and then by using these deflection angles, you can start setting up your theodolite at the point T1, um, locating the point B, setting the angle to 0, and then you can keep on adding the angles in your theodolite. You can cite those points, measure the chord, and keep inserting points in the ground for the curve. So what we usually do is that we put in pegs in the ground, and once you're done with the whole procedure, you're left with the whole shape of the curve, and the pegs at regular intervals give you that shape. But before that, you need to make that table that we made for the simple circular curve, the table to set out the curve in the field. So that gives you um, the addition of angles at every point, at every distance, what should be the deflection angle. So it gives you that. So that is it for the compound curve. Next time we'll start with the reverse curve.